and soft tissue areas so that you know exactly how to build this patient's prosthesis. The next step is pulling the plaster model into a plastic socket. So you take the model and you drape it with a plastic sheet that's heated up to an extremely high temperature. That sheet will then mold to that plaster model, and once the plastic has cooled and hardened, you can break out that plaster model and you have a prosthesis. Then you can modify and make any necessary adjustments, but those are the basic steps of building a prosthetic leg. Another aspect of my research this year has been on the principle of osseointegration. Now, osseointegration is a relatively new surgical technique that's only recently been approved by the FDA for use within the United States. What happens is a patient, typically with an above-knee amputation, is able to have a metal pipe inserted into their leg at the side of the amputation. By inserting the pipe directly into the bone, this makes sure that they don't need to use a socket anymore. And because sockets typically come with a lot of fit issues and structure issues because they can grate on the patient's leg, osseointegration is a revolutionary technique for addressing concerns brought up by a socket. Now, the problem associated with osseointegration is the fact that there's a lot of risk that the bone will fracture or that the patient could otherwise harm themselves. For example, because many patients with prosthetics are older patients, if they have a bad fall or an accident and land incorrectly on that leg, that pipe could further fracture their bone. And if that happens, the consequences could be very bad. As a result, what scientists are actually doing right now is investigating how antlers on deers work. Because on deer, the antler is made of bone and it protrudes from their head without any risk of infection. So researchers and engineers want to replicate that very technique inside humans as well. This moves me into my next major topic of study. I really wanted to focus in on how do engineers anchor these prosthetic devices to their patients, and the answer is suspension systems. Now, the first form of suspension system that I'm going to mention is a suction. And now what a suction does is it essentially pushes air out through a valve on the outer edge of the socket. Because it only serves to push air out, it's a relatively passive form of suspension. And what happens with this is that it's very easy to get messed up or fail, because if a hole appears on the sleeve going over the suction, the entire purpose would be negated, because a hole would mean more air entering the socket and leaving the socket than you want it to happen. So with a suction, it's not as functional for patients that have a high risk of being too active and getting a hole in their sleeve. Another typical form of suspension is a shuttle lock. Now, with a shuttle lock system, you have the socket, and at the bottom of the socket, there's a pin. There's a hole for a pin. And what you need for this form of suspension is essentially a gel liner and the socket. So first, you put on the gel liner, you pull it over your residual limb, which is a limb on which the socket rests, and at the end of that gel liner, there'll be a pin. And that pin gets inserted into the bottom of the socket. Once you hear a click sound, that means the shuttle lock has engaged and that the suspension is essentially inactive. So the biggest problem with the shuttle lock system is the fact that there's a lot of dead weight hanging off the edge of your limb. Consider this: whenever you hold something close to you, you don't feel how much weight it is, because it's close to you and the radius isn't very big. But the further and further you hold something away from your body, the heavier and heavier it feels, because it's so far away from your center of mass. The same principle applies to a shuttle lock, which is typically why it serves as an individual's first transitory prosthesis, because there isn't as much of a concern for how well the socket fits on the leg. And because the residual limb gradually changes sizes during their first year, this is really helpful. And the last form of suspension that I'm going to mention is a vacuum. Now, a vacuum is very similar to a suction in that it works with the air within the socket, but with a vacuum, it's much more active because it really pulls that air out through a pump. This pump could either be electronic or mechanical. In recent years, it's becoming more and more common to use an electronic pump because you just attach it to the bottom of your socket right here below your knee for a lower limb amputation, and it registers whenever there's too much air, whenever there's too little air. Any minute changes in air that need to be made, the pressure is automatically adjusted by the system. This form of suspension is also better with skin issues and optimizing blood flow. Another major issue similar to the suction is the fact that if a hole appears within the sleeve, the system will fail as well. After all this research I conducted on suspension systems, I really wanted to focus in on how could I incorporate all of this and really figure out what does this data mean. And what I decided to do was focus on this topic for my original work. In my original work, I analyzed the effects of various forms of suspension system on user satisfaction. I came up with a hypothesis that below-knee patients would experience greater comfort and functionality than those with above-knee prosthetics, and I decided to put this to test by gathering data from real individuals wearing prosthetics. I contacted the director of the Dallas Amputee Network, and I asked her for information on her patients. She sent out my survey link, and soon I got 25 responses, and I was so happy with the data I collected. This way, I was able to compare all the data I had, but first I had to come up with a method. What I finally decided to do was compare above-knee data against below-knee data, because these two types of prosthetics are pretty different in that they accomplish different functions. An above-knee prosthetic has to include a microprocessor knee, while a below-knee prosthetic does not. First, I'm going to start with my patient demographics. I had a typically older population of individuals who are 50 plus, and this makes sense because the most common cause for getting a prosthesis is diabetes. And diabetes is typically seen in older patients. Another aspect I looked at was what type of prosthesis. About 2/3 of my respondents used a below-knee device, and only a third used above-knee. And this also makes sense because below-knee is much more common than above-knee. The last thing I analyzed was how long each of these patients had been using their current prosthetic device. And what I found out was the majority of these had only been using them for less than a year or 5+ years, which tells me that there could be a great difference between a transitory prosthesis, which is that first prosthesis I was mentioning before, or a much more used prosthesis, which means that the individual's residual limb isn't changing size so rapidly anymore. So that was something I definitely had to consider when analyzing my data. That brings me to my above-knee data. When looking at this graph, you can easily see that there's a lot of variability in my responses. There's responses all the way from the lowest category, which is 1, all the way up to 10, which tells me that above-knee devices have the ability to fit really well or really poorly. I want to take one category in particular and a closer look at it, and that is the ease to walk up and down stairs. That category is one of the lowest rated categories on that graph, and as I thought about it, it made sense. Because a above-knee device needs to have a microprocessor knee, any issues incorporated with that part will greatly impact how well a user is able to walk. And that would also impact another category, which is functionality and frequency of usage. In comparison, my below-knee data is much more concentrated at the higher end of the scale. You can clearly tell that the responses for the categories from 7 to 10, which are on the highest end of the scale, are much more in quantity than in the above-knee data. One of the categories that is most commonly seen is the fact that there is a lot of responses for frequency of usage in the highest category of 10. And because below-knee devices have been researched in greater depth because they are much more prevalent within society, it makes sense that these users are able to get a smaller level of variability within their usage, so they're able to use these devices more. And what that tells me is that below-knee devices and prosthetics are able to accomplish the purpose they need to, which is helping a user get back some of their functionality and go back out and live their lives. Overall, from my original work, what I learned was that my hypothesis was in fact true. The below-knee data clearly had much higher ratings than above-knee data. And because above-knee, I also had a smaller population of responses for above-knee, that could be somewhat the reason for this, but I think the main cause was the fact that below-knee devices are just much more steadfast in their usability and functionality because there's just been a lot more research going into it. However, that trend is recently changing because above-knee data, there's much more techniques coming in for above-knee prosthetics, such as osseointegration, like I mentioned previously, and another one called targeted muscle reinnervation. Now, after I concluded my original work, I wanted to look back on and see what all I had accomplished so far in ISM. I had learned how to make a socket, from taking a patient's leg, to casting it, to making it a plaster model and then turning it into a plastic socket. I was able to see this in person every single step of the way, thanks to my mentor, Mr. Wilson. I also became aware of revolutionary techniques, such as osseointegration, targeted muscle reinnervation, and even 3D printing. With 3D printing, these devices become cheaper and easier to mass produce, so a prosthetist doesn't have to spend so much time building a device and can spend more time treating their patients. And what all of this showed me, from every single step of the way, from the research interviews, from the research I conducted on my own, to choosing my mentor and the mentorship experience I've had so far, I've learned just how important it is to be curious and always have an open mind, because you never know where the next revolutionary technique could come from. This leads me perfectly to my quote for this year in ISM. What material success does is provide you with the ability to concentrate on other things that really matter, and that is being able to make a difference, not only in your own life, but in other people's lives. Oprah Winfrey. Just like this quote says, I want to use all the knowledge I have gained this year, and will gain in the future, to actively help others and improve their lifestyles. This field gives me the ability to directly impact the world around me, and the possibilities and opportunities are truly endless for a biomedical engineer. Even though my ISM journey has now concluded, the lessons I've learned about professionalism and the experiences I gained through my mentorship with Mr. Wilson will stay with me forever. I now know that I want to pursue a career in prosthetics and biomechanics in the future, and I can't wait to further my knowledge and continue my education at the University of Texas at Austin next year, where I will earn my bachelor's degree in engineering and hopefully continue my research in this field. In conclusion, biomedical engineering combines creativity with engineering principles to advance medical care, and I personally can't think of a better way to improve life than through technology itself. Even though this is the end of my presentation, I would like to take this opportunity to thank my mentor, Mr. Wilson, for helping me see how prosthetics are made from the very initial phases to the end, and for being an incredible guidance throughout this entire crazy journey. I would also like to thank my parents and my friends for all of your support and encouragement. You helped me really challenge myself, and as a result, I was able to accomplish everything I could possibly hope to have gained through this ISM experience. Thank you.